We'll pick up where we left off the last time. So statistics, like any other science, has some jargon, but we'll keep it to a minimum and only give you what's necessary. First of all, what's an observational unit? Well, an observational unit is the thing on which you gather your data, right? You collect your data from observational units. The thing to bear in mind is they are not always physical things. Most of the time, yes, observational units could be people, animals, the trees, plants, but they could also be abstract things like time points. For example, you every day at 7 p.m. you go out and measure the temperature, let's say. So the time points would be the observational unit, right? It's not your house, but it's the time points. Or you could even have more abstract kinds of observational units, like, for example, basketball free throws. You want to see every time you try a free throw whether you make it or not. So each trial is an observational unit. All right. So just bear in mind, observational units need not always be physical entities. What's a variable? Well, a variable is what you measure on the observational unit. So an example would be height, weight, year in school. So by looking at these variables, I think you can guess that the observation units should be people or Hope students, right? In this case. Which of the two here are quantitative? It's actually height and weight. And how do you tell height and weight are quantitative? Because it's quantitative if doing arithmetic operations on that variable makes sense. Okay, so it makes sense to add up people's heights. And then you could find a range of heights, you could find the average height, and you could do the same for weight. It does not make sense to add up people's years in school, even if you number them as year 1, year 2, and so on, right? You can't average someone is in year 1, someone's in year 2. It doesn't make sense to average the years in school. So an important distinction is, even if numbers are used for the years in school, it doesn't necessarily mean it's quantitative. The number is just a tag. So one way to tell when something is not quantitative, is categorical, is even if it's using a number, can I replace that number with any other tag? For example, replace 1 with freshman, right? If you can use words to represent variables, values, that indicates that the variable is categorical. So a categorical variable is a variable whose outcomes are category designations. For example, what year are you at Hope? You'd say, well, I'm a freshman, I'm a junior, whatever. And were you born in Michigan or not? The answer is either yes or no. So the kind of answers that you give already tell you what kind of variable it is. I mean, if I asked you whether you're born in Michigan or not, you don't say 7. Yeah, that makes no sense. You say yes or no. So if it's a yes or no outcome, that tells you that being born in Michigan is a categorical variable. If I asked you how tall you were, you don't say yes, right? You give a numerical answer. So that tells you that height is a quantitative variable. The last jargon for this slide is distribution. That's just a word to mean what do the variable values look like, right? The pattern, the shape of the variable's values. A few more definitions. What's a population? By definition, a population is the collection of all possible observational units. So here's a simple example. All Hope students is a possible population, right? It's the complete collection of every Hope student. A sample is any subset of a population. So the natural one would be all Hope students who are in my class, in this class, would qualify to be a sample because it's a subset of the population. What's a parameter? So a parameter is a number and it tells you something, it summarizes the population. For example, what's the mean height of Hope students? See, the mean height is a number. So I would say you need to distinguish between the parameter and the population. Learning statistics in English is a little bit easier because a lot of these mental alliterations work very well. P with P. So a parameter is a number that summarizes the population. P with P. Parameter, population. They're not the same thing. Population is a set of things, a set of observation units, but a parameter is a number that summarizes those observational units, all right? So distinguish between the two. They're connected, but they're different. A statistic is also a number. It's a number which summarizes a sample, all right? So you see P with P, parameter summarizes population. The statistic is also a number. It summarizes a sample. Here's an example. The mean height of Hope students in my class, in this class. So what's the difference between a parameter and a statistic? Statistics are known because you can find them out, right? You have students in your class, you can find the average height. It might take a while, but you can do it. But in contrast, parameters are typically unknown. Why? Because you don't have access to every single person in the population or thing in the population, all right? For example, the mean height of Hope students, you probably don't know this answer because do you have access to every single Hope student? I don't think so. Until you have access to every single Hope student, you cannot identify what the number is for the mean height of the population. All right? That doesn't stop it from being a number. It's still a number, but you just don't know what it is. So, as a science, statistics' job is to make and test statements about parameters. Right? Inferential statements means statements that infer values of what the parameter could be. Right? To infer is to make an intelligent guess. Right? To make a statement guided and informed by knowledge, not just a random guess. Why do we not make inferential statements about statistics? Well, because statistics are always known, right? So there's no need to infer or guess what their values are. There's no need to say, oh, I think the sample mean height is in our class is 70 inches. You don't need to guess, right? It's something that you can calculate and know. You only make inferential statements about parameters. And so this course, a statistics course, is basically about the kinds of statements you make about parameters, and then how do we test from the data that we have whether there's any evidence to support these statements. So at this point, you should try group work 1. It's 5 minutes long. I don't think you'll need all the 5 minutes, but you should pause the video and try group work 1 and then come back for the rest of the video. So we look at chapter 1 now, and we are talking about, we're doing a quick revision of these very important definitions. So parameter is a number which summarizes the population, P with P. Example, a mean height of Hope students would be an example of a parameter. It involves all Hope students, and the number that we're interested in is the mean height. Statistic is also a number. It's a number which summarizes a sample, and an example would be the mean height of students in our class. Statistics are known because they can be calculated from an observed sample, but in contrast, almost all of the time, parameters have numerical values which are unknown. This is because we rarely have access to every single person in the population. If you did, then the parameter would be known. So I'm going to introduce some symbols for parameters and statistics. Some you may have seen before, some may be new to you. So the commonly used symbol for the unknown population mean, right? The mean is a number. The population mean is a parameter. It's the mean that belongs to the population. We use the Greek letter mu. It looks like this. Why? Because mu is the Greek m. So we are talking about a mean. So the Greek letter mu is used for this unknown parameter. A commonly used symbol for the calculated sample mean, which is known, which we get to calculate. This one you may have seen is x bar. The size of a sample, we commonly use n. And one thing to note is in Hope, especially, we try to be consistent. Anything that is known gets an English letter, so x bar and n, right? Anything that's unknown that you don't know the value of, we use a Greek letter, right? We are consistent with that. A commonly used symbol for the spread of the data, we talked about the spread before. What was that? One example is the standard deviation. That's calculate. You can calculate that. So we use a symbol S for that. So we use an English letter S because the standard deviation is also something you can calculate from the sample. And as I just said, here at Hope, we use English letters for known calculated statistics from samples, and we use Greek letters for unknown population parameters. So in our last class, we talked about the Galton board and what it actually does. We know that the Galton board basically replicates what happens when you collect many different samples from a population. Each time you calculate a mean, you'll find that there are differences between the means that you get because you get different samples, right? If you sample many times from a population, you get different samples, and each sample gives you a different mean. So there's variability not just in the samples, but even the means that you calculate are variable. So the Galton board basically shows you the distribution of the different means that you could get when you sample from a population, right? You also note that a Galton board has a center, right? That's where all the balls fall in, right in the middle. So there's a fixed central value on the Galton board. So as I just said, these different means from different samples are represented by the balls falling through the board and landing at the bottom. Now, you will note that most of the values of these means tend to fall eventually near or far away from the center. If you have looked at the video, you'll find that most of them fall near the center of the Galton board. And we label the central value mu. Okay? Then this mu is the population mean. A few balls, however, will fall far away from the central value. And we also noted last time in our last video that the shape of the small balls in the Galton board forms a bell curve. And it looks something like this. So you see, most of the balls eventually end up near the middle where mu is. But of course, there are some who are farther away, but not many, right? Farther away from the middle. And the overall shape is a bell curve. So the Galton board is a way to, in a way, explain what is the distribution of different means from different samples when you sample from the same population. So we can tell how rarely any particular mean value is by checking to see whether there are many balls on the Galton board more extreme than that value. So for example, we have every Galton board has a center, right? And that center is mu. But if you want to see whether any particular sample mean value, let's say x bar, right? If it's something that happens quite a lot on the Galton board, then you would expect there will be quite a lot of red balls in that zone. So if the proportion of balls in the red zone is large, in other words, there are many balls that are in that zone near the X bar that you saw, then it means that kind of mean, when you sample many times from a population, it's quite often that you see means like that. However, if you find that your mean is way on the left side, and there are not many balls in the red zone, then it means that that particular value of a mean is quite rarely observed when you sample from a population. It's extreme. Now, it doesn't just have to be the left side. It's also true if you have a value of X bar that is on the right. So you have the Galton board, and then you have some particular value of X bar, all right? It's larger than the center, so it's on the right. So you can check if there are not many balls on the right side of X bar, then it means that that value of the mean is quite rarely observed. However, if there's many balls on the right side of the X bar, it means that that value is quite common to be observed on the Galton board. So let's give you a practical example with some numbers. Let's say we want to test whether the population mean height at Kelvin is 72 inches. All right. Now you may ask, where did 72 come from? Actually, this could be any number that you want to test. You make a claim, or maybe you heard it from someone. The average height at Kelvin of students there is 72 inches. Okay, so you want to test this. As I said, the all of statistics is basically trying to test inferential statements about a parameter. You don't know whether it's 72 or not. So you're trying to test whether this is true. All right. So of course we don't have access to everyone, but we have a sample of people from Kelvin. We have one sample. So our Kelvin sample mean was X bar is 74.6. So I hope you realize why 74.6 is given the symbol X bar. It's not new. This is a sample mean. You have a sample of people from Kelvin. That mean was 74.6. The thing you're trying to test is whether the population mean value is it 72 or not. So you need to make a Galton board. And you make a Galton board whose middle is, yes, 72, not 74.6. The Galton board is always centered at the value of the population mean. And so now we want to test, okay, if the population mean is 72, we pour many balls through the Galton board, like what you saw in the video, and then you check whether 74.6 happens a lot or not. Look at the red zone. How many balls fall after 74.6? All right. But you can see that it's quite limiting to use a Galton board, or it's not the easiest thing, because every time you want to test a different mean, you have to make a new Galton board with a new center. See, this one is a Galton board with a center 72. If I wanted to test something about the population mean height at Hope, for example, and let's say I wanted to test whether mu is 74 or 70 or whatever, I would need to make a new Galton board with a new center. All right. Also, you notice that, let's say we didn't have a Galton board. All we have is the sample mean value of 74.6, and the central value is still 72. Do you realize we can't tell whether 74.6 is rare or not? You don't have a red zone. If you don't have a Galton board, you don't have the balls falling through it to form the bell curve. You have no idea whether 74.6 happens rarely or not. Yes, it is to the right of 72. Everyone knows that. But how rare is it you need a Galton board and you need a red zone to see, oh, not many balls fall there. So it's quite rare. It's stuff like that. So distance alone cannot tell you whether something is rare or common, right? For example, you may know, or someone tells you, oh, the average people, when they eat out, the average price people spend for dinner in America is $25, let's say. It's probably not that anymore, but let's say it's $25 on average, all of America. Now you get a sample of people and you find that their average for dinner is $50, something like that. Is that extreme or not? It seems extreme, but do you realize that without a Galton board and looking at the distribution of all possible means that you could get from population, it's impossible to tell how extreme $50 is, right? Yes, it is more than 25, but is it extreme or not? So you need to take into account all the other mean values that you could see, and that's why you need to take into account the spread of the mean values, which is what the Galton board does for us. And you recall from the last class, the spread of means is called it's two words. Also, the word standard is there, but it's not a standard deviation, it's a standard error, if you remember. Right? Now, the good news is this. There's no need to make all these Galton boards. There is no need. All right? All you need is actually to use a standard Galton board. All right. Now, where is this standard Galton board? I'll show you. If you go to our Moodle page, you'll find that there's a table called the T distribution table. This is the standard Galton board. Do you see the Galton board at the top, right? The density curve, yes. And I know we call it a red zone. Here's a blue zone, right? It's equivalent, all right? And you see a whole bunch of numbers. I'll get to that right now. To use the standardized Galton board, you need to compute what's called a standardized T value or T statistic. This is defined by T equals X bar minus mu divided by S over root n. You will notice that all these ingredients I've defined for you. X bar is the observed sample mean that you have. S is the standard deviation of the data. N is the sample size. And mu is the thing you want to test, central value. If you compute this standardized T statistic, you can use the standard Galton board, which is the T table. All right. So to give you an example, I want to know something about the mean sleep time here at Hope. And let's say I want to test whether on average Hope students sleep 9 hours a night, on average, or do they sleep less than 9 hours a night? So the population mean sleep time of Hope students is not known. So we give it symbol mu. What am I claiming? Well, I'm claiming mu is 9, or alternatively, mu is less than 9. So I want to see if there's evidence that really, on average, Hope students sleep 9 hours a night. Right? Don't worry too much about the HOHA symbols. This just means null hypothesis and alternative hypothesis. We will get to that in the next class. More important to focus on is see what this statement says. It says that the mean time on average in the population at Hope is 9 hours of sleep per night. So I got the class to contribute what their sleep times were. And here it is. If you go to the spreadsheet, we have a data scratchpad also linked on Moodle. It's the section 7 or section 8, but I'm using, for illustration purposes, I'm using the section 7 data. So you see the whole class, they put in these data points. These are the number of hours they slept. All right, last night I asked them. And you can use Google Sheets to calculate the three things that you can calculate from the data. Okay, you know that you want, look at the t statistic. The t statistic requires x bar, s, and n. All right. So I will show you now quickly how are these things found. I think sample size n needs no explanation. You just count how many people there were in a sample. There were 16. How do you get x bar? Well, I'll show it here. You go to an empty cell, type equals average like that, and you select the cells that you want to find the average of like this. Then just hit enter. That's the average. All right. How do you find the standard deviation? Well, you go equals STDEV, parentheses, select all the cells that you want to find the standard deviation of. This gives you your value of S. See? So you have your X bar, and you also have your S. We have N, of course, so I'll just reproduce this from up there. So you see, now don't worry if you can't remember these things. We will be dealing with Google Sheets the whole semester. This is just your introduction. I will show you this again at some other point. But anyway, I'm showing you now. And here are how you find those three values. So all you need to do in order to calculate the standardized t statistic is, well, plug these numbers in and calculate what this is. All right? So what's the sample mean? You fill it in your notes. The sample mean was 7.9375. The symbol we use when observed mean is, right, x bar. From our class, we found that our sample standard deviation was S, and that's 1.8786. All right, so you can fill that in. 1.78, sorry, 1.8786. And what's the symbol for the sample standard deviation from your data, from your class sample data? Yes, it's S. And of course, the symbol for the sample size is correct. And we know that's 16. Okay. Now remember that mu, Google Sheets cannot tell you. Why? Because mu is what you want to test. Google Sheets can only tell you things about the data that you see. What you want to test is what you want to test. And remember, we wanted to test whether mu is, if you go back to our slide, yes, we wanted to test whether mu is 9, right? We wanted to test whether mu is 9. So the value of mu that we want to test is 9. All right? Now you calculate this. And I would encourage you to take your calculator and pause the video and actually put in those numbers and get your t statistic. Now I'm going to use Google Sheets to find out what it is. If you don't like it, you can ignore this part. I'll just show you how you can actually compute this on Google Sheets. You can use a conventional calculator if you like. So we want to calculate the t statistic. How is this done? You go to an empty cell, type equals, parentheses. Now it's x bar minus mu, which is 9, over S over the square root SQRT of, well, 16. That was our number of people in our sample. Put the whole thing in parentheses, and there you have our class value of t. So keep note of that. If I encourage you to use a calculator, check your answer. Do you get minus 2.2623? Right? You should. Minus 2.2623 like that. So once you have this, I'm now going to show you how to get the standard Galton board. So go to our T table. There's one small thing I must point out. There is this thing called the degree of freedom. I don't want to dwell too much on it right now to break the flow of the class. But basically, you need to go one less than the sample size. Basically, look at row 15. Look at the one with 15. 16 less 1 is 15. According to the rules, you go to the one that is one less. The degree of freedom to use is one less than the sample size. Okay, so what was our value of t? Our value of t was minus 2.262, right? So go to the t table and have a look. Where's minus 2.262? So you'll find that minus 2.262 is actually between these two numbers. Do you agree? Minus 2.262 is between these two. These two correspond to what area? The blue area. Okay, let me just try to highlight these to see. Those two values are between these two areas, 0.025 and 0.01, which basically means the blue area here, when you are at minus 2.262, is something between, what's this, 1% and 2.5%, right? 1% and 2.5%. These are quite small, right? It means that your area, the tail area, when you see that, is quite small when your T that you observe on a standard Galton board is minus 2.262. So the last thing I want to introduce, so does it mean that minus 2.262, that score, does it happen quite rarely when on a Galton board? Quite rarely. Only about between 1 to 2.5% of the time. So that's quite rare. And so that kind of thing, this kind of area, the blue area, is called a p-value. You may have heard this phrase before. It's called a p-value. And we will revise all these things in our next class. Okay, so that's it for this video.